Welcome to the Introduction to Process-Informatics series. In this first chapter, we will explore how data-driven approaches are transforming manufacturing excellence across industries. Process informatics combines domain expertise with advanced analytics to understand, optimize, and control industrial processes. By the end of this chapter, you will understand what process informatics is, how it differs from materials informatics, and why it matters for modern manufacturing. Process informatics encompasses 5 core activities. Data collection and analysis gathers sensor readings, operating conditions, and quality data, then looks for hidden patterns. Process modeling builds quality prediction models using machine learning and soft sensors. Process optimization improves yield, reduces energy consumption, and raises quality by finding better operating conditions. Process control turns real-time data into automatic control action. And anomaly detection identifies abnormal states early before they become upsets. These activities work together in a continuous cycle to drive process excellence. Process informatics and materials informatics are complementary disciplines. Materials informatics asks what to make, focusing on composition, structure, and properties. Process informatics asks how to make it, addressing temperature profiles, reaction times, and equipment settings. Think of it like cooking. Materials informatics is the recipe ingredients, while process informatics is the cooking instructions. Together, they provide complete manufacturing intelligence for optimal product development. Processes in the process industries fall into 2 main categories. Continuous processes operate 24/7 with constant input streams, like petroleum refining and power generation. They produce steady-state data streams. Batch processes operate in discrete cycles with start and stop phases, common in pharmaceuticals and specialty chemicals. Each batch is a complete production unit. Understanding these differences is crucial because they require different data analysis approaches and present unique optimization challenges. Process informatics applies across diverse industries. Chemical and petrochemical industries produce bulk chemicals and fuels. Pharmaceutical manufacturing requires strict quality control and regulatory compliance. Food and beverage processing prioritizes safety and consistency. Semiconductor fabrication demands nanoscale precision. Pulp and paper production involves continuous large-scale operations. Each industry has unique challenges, but all benefit from data-driven process optimization through shared fundamental principles. Why do we need process informatics? Because industrial processes are inherently complex. They are multivariate, with dozens of interconnected variables affecting each other simultaneously. They are nonlinear, meaning doubling an input does not double the output. They have time delays, where changes take minutes or hours to show effects. Traditional approaches struggle with this complexity. Process informatics provides the mathematical and computational tools to handle these challenges effectively. Modern plants generate massive amounts of sensor data. Temperature sensors track thermal conditions. Pressure gauges monitor system forces. Flow meters measure material movement. Level sensors indicate tank contents. Concentration analyzers measure chemical composition. pH meters track acidity levels. A typical plant may record 10,000 or more measurements per minute. This data richness is both an opportunity and a challenge that process informatics helps us navigate. Quality measurements like purity and yield are critical, but often difficult to obtain in real time. Traditional laboratory analysis can take anywhere from about an hour to a full day, and up to a week for impurity analysis, creating significant delays. Soft sensors solve this problem by using machine learning models to predict quality from easy-to-measure process variables like temperature, pressure, and flow rate. They provide instant quality estimates, reduce laboratory costs, and enable continuous optimization. This is one of the most impactful applications of process informatics. Let us look at real-world impact. In one chemical plant, process informatics improved yield from 85 to 90%, generating roughly 500 million yen of additional profit per year. In another case, energy optimization reduced consumption by 15%, with significant environmental benefits through reduced carbon emissions. These examples demonstrate that process informatics delivers tangible value. The return on investment typically justifies the effort within months, not years. To summarize Chapter 1, process informatics enables data-driven optimization of manufacturing processes. It differs from materials informatics by focusing on how to make products rather than what to make. It handles the multivariate, nonlinear, and time-delayed nature of real processes. Sensor data provides rich information streams for analysis. Soft sensors enable real-time quality prediction. In Chapter 2, we will dive into data preprocessing and visualization with hands-on Python coding using Pandas and Matplotlib.